Hello and welcome to this Matlab tutorial. My name is Felix. I work at the Auditory Cognition Group at Newcastle University, and today we're going to talk about one of the most important questions during data analysis, and that is whether your data actually contain a proper signal or whether you have actually just recorded noise. I'm going to walk you through a few options in Matlab to show you what's possible and what you can do to evaluate your data. And the data I'm working with today is cortical multi-unit activity that I've recorded in the auditory cortex in response to the repeated presentation of a white noise burst. Okay, let's get into it. I have imported and visualized my data. You can see the number of trials on the y-axis and time on the x-axis. The white noise bursts I presented were 200 milliseconds long with sound starting at time bin 200. And the color code of this plot actually shows you the normalized neuronal response. What you can already see by just eyeballing the data is that we get quite consistent stimulus-evoked activity across trials. And the purpose of this video is to show you how you can actually test whether this is a proper signal that you've recorded or whether it's just a random noisy fluctuation in your data. Okay, let's go to option 1. Simply test the activity in a defined time window with a statistical test. This is the easiest, but in my opinion, also the most boring option you can choose. First, we're going to define the onset time bin of our stimulus, which is at time bin 201. We then also define the duration of the time window we are interested in, which is 100 milliseconds in this case. And next, we are simply averaging across the first 100 milliseconds after stimulus onset. So from time bin 201 to time bin 300, and we average over the time domain of all trials. And this gives us a distribution of normalized neuronal activity in the stimulus onset time window. Okay, we're going to do the same thing for our baseline activity. So here we simply average from our first time bin to the stimulus onset at time bin 201. And yeah, we do the same thing. We average over the time domain and we get a distribution of normalized neuronal responses during that time window. Okay, and once you have defined your two distributions, you can then simply do a statistical test like the Wilcoxon-signed rank test, or an ANOVA if you have several parameters like sound intensity and frequency, or in the visual domain it would be orientation and contrast, for example. And then you'll get a p-value that tells you whether those two distributions are actually significantly different from each other. We can also visualize those two distributions, and you can clearly see they are not at all overlapping. So it's not surprising that the p-value is quite small, because the neuronal activity during sound presentation is far higher compared to the average activity during the baseline period. Let's go further to option 2, which is the evaluation of the signal to noise ratio. This works in a slightly different way. Here you first define the average activity across your trials. You can visualize that. And it would look like this. So again, the x-axis shows you time, the y-axis shows you normalized firing rate. And during the first 200 milliseconds you have your baseline period. It fluctuates, but mostly around a steady level. And then you have your stimulus evoked neuronal activity. Okay, so the way this works is that I define several time windows during which I compare the stimulus evoked activity with the baseline activity. Here I'm defining my step size. As you can see, I simply start 10 milliseconds after stimulus onset, and then I go in steps of 10 milliseconds up to 100 milliseconds after stimulus onset. The length of this time window is defined as 49 milliseconds plus the first time stamp that you can see here. So the time window is 50 milliseconds long. I then extract the average neuronal activity during the baseline period, and also the standard deviation, the baseline variability. And I then loop through each of my defined time windows. Okay, so let's define that for our first time window. The start of that time window is defined by my onset timestamp plus the offset that we have defined up here, and this time window then is 50 milliseconds long, so it runs from 211 milliseconds after stimulus onset to 260. We average the activity in this time window, it is 0.74, and we then subtract the mean activity during the baseline activity and divide by the standard deviation in order to get the signal to noise ratio, which in this case is about 15.6. And we do that for all of our time windows. And as you can see, signal to noise ratio is quite high for all of the time bins. And what you can do is you can either look at all of those time bins or for only one time bin that you're particularly interested in, or you can simply take the mean over all of those time bins, which then gives you the average signal to noise ratio during your onset transient. In this case, it's 14.2, and as a rule of thumb, you can assume that if you have a signal to noise ratio that is larger than 3, then you generally have a good signal. Alrighty, the next option number 3, is to detect a threshold crossing. And this is actually my preferred method because it doesn't only tell you whether your signal is significantly different from the baseline period, but it also tells you when exactly the onset transient crosses the significant threshold, which gives you the onset latency of your neuronal response. So the first thing you need to define for this procedure is the threshold. You normally would take about 3 or 5 or 6 standard deviations of your baseline activity. In this case, I've used 3 standard deviations, but yeah, you can use any value that you like over here. Normally, if your signal crosses 3 standard deviations of the baseline activity, then you usually have a proper neuronal response. You then also define the number of time bins that need to be significant subsequent to the first threshold crossing. So you detect the threshold crossing in time bin A, and you then want to have the 9 time bins after that to be significant as well in order to define time bin A as the onset latency. So it's the timestamp that you detected the first threshold crossing plus additional 9 time bins. We here define our sound duration, which is 200 milliseconds. We also define a vector of where to find our baseline activity. Okay, so your threshold is then simply the average activity during your baseline period plus n times the standard deviation during the same period. And you do that in either direction. You add it up and you subtract it, and that way you get a threshold in either direction. Okay, so if your onset transient crosses either this or that number, then you have a significantly different neuronal activity in response to your stimulus. And similarly to the signal to noise ratio, you need to define a time window, but this time you have a time window that you slide through the time domain. Okay, in my case, we start at the stimulus onset timestamp, and we move our time window through the entire stimulus presentation period minus the time window duration, which in our case is 10 milliseconds. Okay, so let's check that for the first window. The position of our time window now covers the first 10 milliseconds after stimulus onset, and for this time window we are extracting the mean activity for each time bin, and we look whether those numbers are actually larger than either the first threshold or are larger than our second threshold, so either the upper or lower threshold. Okay, in case of the first time window position, you can actually see that the neuronal activity during the first 10 time bins is actually not above or below our defined thresholds. What we're doing to quantify this is we're simply summing this vector over here, which in this case is 0, but theoretically you want to check whether it's 10. And once this vector is 10, you simply write down the time window position. So let's do that. We're going to loop through all of our time window positions, and then you get a vector where you see the first time bin where the subsequent 9 time bins were significant as well. And as you can see, after about 29 milliseconds after stimulus onset, we get our first significant response. So again, I really like this procedure because you not only get this binary yes, it is significantly different, or no, it's noise, but if it is significantly different, you also get the onset latency for free as well. Okay, one thing that I've learned over the last years is that it's always worth to look at the variability of your signal across trials. So in this plot, for example, I'm just showing you the standard deviation for each of the time bins, and you can clearly see that the variability across trials increases after stimulus onset. So it's always worth to check the variability of your data. You can also visualize that in a few different ways. For example, you can define the standard error of the mean by just extracting the mean activity for each of your time bins, taking the standard deviation, and then dividing the standard deviation by the square root of your trial number. And you then center this around your mean. You can also define your confidence intervals by bootstrapping the mean activity for each time bin. You need to define the number of repetitions that you want to do, and then this function over here bootstraps you the 95% confidence intervals for your mean for each of the time bins. For visualization, you then take the length of your signal, you define your x ticks and your y ticks for both standard error and confidence intervals, and you can then simply plot this with the fill command. The shaded area here corresponds to the 200 millisecond stimulus presentation period. The onset latency of our neuronal response is marked with the dashed line over here. The black line shows you the mean activity averaged across trials, and the shaded areas behind that show you the standard error of the mean in gray and the 95% confidence intervals of the mean in red. And it's always very important that you visualize the variability of your data in addition to the averages you are plotting. Okay, the last thing I want to show you, which is kind of related to the variability section we've just discussed, is the receiver operating characteristic. This is a very handy tool you can use to define how overlapping two distributions are. For example, for our stimulus presentation period, we can average the activity in the time domain and define this as our first distribution, and we can do the same thing for our baseline activity. So we do get two distributions that in our case show us the mean stimulus evoked activity for all of our 30 trials in blue, and the baseline activity for all of our 30 trials shown in red. And as we've seen before in the box plots, those distributions are not at all overlapping, which is why we are not using it in this example. Rather, we are simulating some data. As you can see here, those distributions are now nicely overlapping, and the way the ROC analysis works is that you have a criterion shown here in black that you shift from left to right or right to left over your distributions. And this is a binary classifier that basically just counts how much percent of each of the two distributions is to either side of the criterion. So you can look that up on Wikipedia by just moving the criterion over your distributions. You can then define the true positive, true negative, false positive, and false negative ratios, which you can also label as hit, miss, false alarms, and correct rejections. Yeah, and what you get then is an AUROC curve that's schematically shown over here that shows you the true positive ratio and false positive ratio for each point of the criterion. Okay, let's go back to our example. Since we're working with normalized data, our criterion starts at 0 and goes all the way up to 1. So we start on this side and then we move this criterion in this step size from left to right, and we evaluate how much of each distribution is to the left and to the right of the criterion. And that is what we're doing here. Again, we take our first criterion, which in our case is 0, and we then look how many entries of distribution 1 are actually larger than 0, which are all of them, and we divide that by the size of that distribution, and we see that 100% of entries in distribution 1 are actually larger than 0. We do the same for distribution 2, and that way we get the true positive rate, which is also called sensitivity, and the false positive rate for the second distribution, which is also known as the inverse of the specificity. Optional, not really needed here in this context, but this is how to get the false negative rate and the true negative rate. But yeah, we don't need that now. Alrighty, so we're gonna loop through each of the positions of our criterion, and we can then plot our AUROC curve. And as you can see, the curve goes up pretty steep, then curves around and approaches 1. And this is usually a good sign. If your two distributions are completely overlapping, you would get just a straight line from 0 to 1. So the more curved your AUROC curve is, the better. You can then evaluate the area under this curve, and higher areas under the AUROC curve indicate more separation between your two distributions. The area under this curve here is 0.92, which is actually pretty decent. Okay, that's all I want to show you today. I hope this video has shown you some tools that you can use to evaluate whether your data actually contain proper signal or whether it's just noise. And yeah, if you find this kind of content helpful and if you enjoyed watching that video, please leave a like, please consider subscribing, and I see you in the next Matlab tutorial. Until then, stay safe. Bye bye.